Ladies and gentlemen, thank you for standing by. The conference will begin shortly. Ladies and gentlemen, thank you for standing by. Welcome to the Instrumented Pavement Recycling Performance on Interstate 64. At this time, all participants are in a listen-only mode. Later, time permitting, we'll conduct a question and answer session. Instructions will be given at that time. If you should require assistance during the call, please press star, then 0. I'd now like to turn the conference over to your host, Jason Dietz. Please go ahead, sir.
Thank you, David. Well, welcome, everybody, and thank you for joining us today. My name is Jason Dietz, and I'm with the Federal Highway Resource Center in Denver, Colorado. And I'm partnering today with the Pavement Recycling Alliance, PPRA, on a series of pavement preservation webinars focusing on pavement preservation by selecting preventative maintenance treatments so we can extend our life and reduce the long-term pavement surfaces using AEMA, ERA, and ISA products and treatments. Today's webinar will focus on Virginia's recycling efforts. All attendees are on mute, but if you can submit your questions through the chat function on your screen, and we will answer them as those time permits. We will be offering PDHs for today's webinar upon request, so please let us know after the webinar if you would like to receive one. I'd now like to introduce our presenter today, Brian Diefendorfer. Brian Diefendorfer is a principal research scientist at the Virginia Transportation Research Council, the research division of the Virginia Department of Transportation, in Charlottesville, Virginia, where he has worked for the past 16 years. He has led the VDOT's pavement recycling research efforts, including studies on I-81, I-64, and the NCAT test section. Of the 3 recent NCHRP projects on pavement recycling, he has been the PI or co-PI on all 3 of these. Brian received his bachelor's, master's, and a doctorate degree in civil engineering from Virginia Tech and is a licensed professional engineer in Virginia. In his spare time, I asked Brian what some of his hobbies are, and he responded saying landscape photography, coaching sports teams with his children, and he's currently training for a short triathlon. So now I'd like to, on behalf of PPRA and Federal Highway, Brian, I want to thank you for your time today, and I'd like to now turn it over to you for your presentation. Thank you, Brian.
Thank you so much, Jason. I guess the first order of business is to ask if folks have gone through and completed the first 3 poll questions. But again, thank you, Jason, and thank you everybody very much for the opportunity to come talk, and thank you for all of those who were able to join into today's webinar. A few quick words as an introduction to pavement recycling. Pavement recycling is one of the tools in the road construction toolbox. Or there are additional tools in the road construction toolbox, and there are 3 primary techniques. Full depth reclamation, or FDR, cold in place recycling, CIR, and cold central plant recycling, CCPR. These pavement recycling methods have been proven and shown to use less resources than the proven construction methods. There are also great opportunities for cost savings as well. They are engineered processes, and they use engineered technology. There's becoming a large history of use of these techniques. Quickly, as a summary of the three processes, full depth reclamation, or FDR, typically treats in the neighborhood of 5 to 12 inches deep as a stabilized base layer, and it can be used as an alternative to reconstruction. Cold in place recycling works a little bit thinner. Typical depth for it is about 3 to 5 inches. And an alternative to it, or it is an alternative to deeper mill and fill and partial depth patching in an asphalt pavement. Cold central plant recycling works in a layer of about 3 to 6 inches thick, and it can be used as a structural base layer. And one thing that I like to add about cold central plant recycling that I will touch on during this presentation is that it can be used to help recycle, materials into a new roadway. And I'll show some examples of how that has been done. So pavement recycling not only can be a cost-effective process, it's also an environmentally sustainable process. Sustainable development has been defined as something that meets the needs of the present without compromising the ability of future generations to meet their own needs. And what comes to mind when we think about this, we think about reusing and recycling material before they're retired. Things that we can be mindful of include the environmental impact, the cost, and then the performance of these systems. My presentation today will touch primarily on the second and third of those, the cost and the performance, but there are certainly sources in the literature that cover all three. So a brief outline for today's presentation. I'll be talking about the Interstate 64 Widening and Reconstruction Project. This is a construction project that was completed, part of it completed here in Virginia, part of it is still underway. I'll talk a little bit about the design and how we proved the design. The way I like to phrase that is the proof is in the pudding, or in this case, maybe it's at NCAT, or the National Center for Asphalt Technology. Again, I'll get into that more in just a little bit. I'll provide some examples of the construction for this project, and then I'll get into talk a little bit about instrumentation, the sensors that we used, how we installed them, and then some preliminary results. Again, as a background, FDR, CIR, and CCPR are three recycling processes. I'll be touching more on FDR and CCPR. The CIR is also a process that's been used in Virginia. There are many states that are using these processes in, widespread applications. And I'll be going into more of those in a few minutes. So first poll question during the presentation: which recycling processes can be used to create multiple layers? And I'll wait just a minute for the results to come through. Jason, I'm not sure why I'm jumping ahead, but anyway.
No, you're good, and hopefully everybody will see the results. And it looks like the number one that came in there was FDR for that answer, Brian.
So what's are the slides jumping ahead for you guys, because they are for me?
Yeah, they are. Somebody's tinkering with them.
So anyway, in terms of the three recycling processes, I see now there's a majority on the CCPR answer C, and that's the correct answer. CCPR can be used to create multiple layers. Typically, FDR and CIR, the materials are placed in one layer, and then there's a surfacing placed on top. However, CCPR, since it's paved as a typical asphalt material, multiple layers of that process can be used and then surfaced with an asphalt material. So poll question number 2, especially for those of you, if you're an agency, answer for your agency. If you're a contractor, I guess answer for the agency you work the most with. My agency uses which recycling techniques the most? FDR, CIR, CCPR, or haven't I used any of them? Hopefully not too many. Option B. So thank you for all those of you who have responded to this poll as well. You can see from the results of this, FDR has been the most commonly used, followed by CIR and CTPR. FDR we have found is really used widespread across the United States. CIR, I guess, is maybe a little more common in certain areas of the country, and CTPR is an option that's come along more recently, and so there's probably only a handful of projects or a handful of groups using CTPR right now, but we hope that will expand in the near future. So I-64 is an east-west interstate route in Virginia, running through the center of Virginia. It covers a little over 320 miles. From the map that I'm showing, the blue star towards the top is Washington, D.C. The yellow star in the middle is Richmond, Virginia, the state capital. And the black arrow pointing down is the approximate location of the project on the eastern side of the state. I-64 is mostly 2 lanes per direction, except in the urban areas where it expands to 4, and I think in some cases maybe even 5 lanes per direction. And it's primarily an asphalt pavement with some lengthy composite sections and a few concrete sections. Here's an example showing a photograph, the portion of I-64 that I'm talking about for this project. This is a before construction view of the site. You can see here the existing pavement was a concrete pavement that was built in the late 1960s. And about 2007 or 2008, there was a widespread maintenance activity where joints were patched and the whole surface was diamond ground in an effort to extend the life of the pavement section. So this served for quite a while, but at some point there was a decision made by the executive level within the agency that this project would experience not only the widening, but also the reconstruction of the pavement. The portion that I would like to talk about is locally known as Segment 2. The I-64 widening processes were divided up into 3 segments, 3 sequential segments working from the eastern side of the project limits, moving towards the west, moving towards the Richmond area. So the first project was Segment 1, was a 5.3 section where the lane was added using what I would say is conventional construction techniques, and the existing the existing concrete pavement was overlaid with asphalt. That work was completed in late 2017. The section that I'll be talking more about today is Segment 2, and it's 7.08 miles in total length, not lane miles, but length of the project. And it's a lane addition and a reconstruction of the existing pavement. The project there started in October 2016 until April of 2019. And again, that's the part of the project I'll be focusing more on in this presentation. There is an ongoing section of the project, Segment 3. Again, lane construction and reconstruction, lane addition and reconstruction of the existing pavement that started in August 2018 and is expected to wrap up at the end of this year, end of 2021. Segment 2 and Segment 3 are both what I would call recycling projects. They use an extensive amount of recycled materials and the cold recycling processes, as well as FDR, CCPR, and FDR. I'll be focusing again more on Segment 2, but Segment 3, the process used is similar. The design is not quite the same, but the process is similar. So for the Segment 2 portion of the I-64 project, the location covered across Newport News, James City, and York counties, and it's very close to Williamsburg, Virginia. In terms of the scope of the project, the scope was to add a travel lane and a 12-foot shoulder to the inside of the existing pavement section, and then reconstruct the existing lanes and a full 12-foot width outside shoulder. The project was awarded at a cost of almost $190 million. And in terms of the traffic volume, this section carries approximately 44,000 vehicles per day per direction and about 5% trucks. So one of the questions that we posed from the research side is, can we design and build a section of roadway using pavement recycling techniques? And I won't go into it much detail here, but it's been discussed by me elsewhere and by other folks that there was a project on Interstate 81 that was built in 2011 that used all 3 of these processes, full depth reclamation, cold central plant recycling, and cold in place recycling. That was built in 2011, and that project was built successfully. And in fact, it has very good performance even to this day. Even this summer will be 10 years for that project. We're seeing excellent performance in that project, and so yes, we can design and build a section using these recycling techniques. Can we also use these recycling techniques to reduce costs and reduce the environmental footprint? And absolutely yes to both of those. And there are many examples in the literature. There was recently an article published by Federal Highway showing environmental costs for this I-64 Segment 2 project. I guess one of the main questions we had, even following the I-81 project, was how long will sections built with these processes last? And for this, we really need performance data. One of the things we were able to do to gather this performance data is to sponsor 3 sections that were built in 2012 at the NCAT test track. This is NCAT, the National Center for Asphalt Technology, that's located there in Auburn, Alabama, along with Auburn University. The 3 sections that we sponsored were N3, N4, and S12. In this case, for the section names, N stands for the north tangent of the track, S for the south tangent, and then the number is just the sequential section going around the track. This slide shows the design for the 3 sections. N3 and N4 are similar except for the thickness of the asphalt overlay, but both include cold central plant recycled material on top of an aggregate base. Section S12 is similar to N4, except for the presence of the stabilized foundation or the FDR layer. And the idea for these sections, they were instrumented during construction, so that way we could quantify the performance of these sections with trafficking. One of the main results that I'd like to share with these sections is looking at the strain at the bottom of the asphalt layers. So again, during construction, strain gauges were placed at the bottom of the CCPR layer in all 3 sections. And these are showing strain results from almost 9 years worth of testing. It's at 29.6 million easels currently, close to 30 million easels of traffic on these sections. And walking through the strain data on here, as we know, a pavement that is stronger will bend less, or a pavement that is less stiff will bend more. So really the sections performed as we expected. N4 was the thinnest of the sections, and it shows here from the strain data that it bends more than N3, which was a slightly thicker section, both on top of aggregate base, however. What really, I think, surprised us the most, and was most intriguing maybe to us, was the performance of section S12, very similar to the N4 design, except for the presence of the stabilized foundation. And you can see with the presence of that cement stabilized layer that the strain value is very low for the section S12, even at high temperatures. The strain that we're seeing from this section really is in the same neighborhood as that is as described as a perpetual pavement section. So this section, really all 3 of these sections are showing good performance. I did get some results from the folks at Auburn and NCAT just a few weeks ago, and you can see in the middle of the data for section N4, there are some high strain values. That information, or those high strain values, started to appear maybe about 2 years ago, and that section is just now starting to crack at close to 30 million easels. However, N3 having a lower strain value overall, and S12 having a much lower strain value overall, those sections are not showing any deterioration at all at the surface of the pavement. And the cracking that is seen on section N4, I would describe as minor cracking, and it's certainly not anything that, if this were on a typical route here for VDOT, it probably would even barely be noticed. It certainly wouldn't be anything that would require rehabilitation yet. So focusing a little more on the section S12. When looking at S12, and counting grout content of the asphalt concrete layers on the surface, 100% wrap in the CCPR and 100% recycled of the FDR material. The average recycled content of that entire cross section is about 80%. And so again, a lot of times some of the research work that we do in my office, looking at high wrap content mixtures, the high wrap may be 40, 50% wrap, maybe a little higher than that. But in this case, I'm thinking of this in terms of the total pavement structure. Well, here the total recycled content is again about 80%. And the thought that we had looking at this is we ought to be able to take this same concept, since it was built at the track essentially materials were pulled out and then replaced with the recycled materials. The same thing we thought could be done on an actual pavement section. And I'll repeat here, the current traffic level in this section S12 is 29.6 million easels as of just a few weeks ago. And it's performing well. We expect that this could go on for quite some time. So using the information we had from section S12 for the NCAT test track, we proposed to the folks in VDOT who were in charge of the I-64 segment 2 pavement design that we could come up with an alternative pavement structure using recycled materials. The two cross-sections shown here, the one on the left is the, I guess, original design for the segment 2 project, consisting of 12 inches of asphalt, a 2-inch thick open graded drainage layer, and an 8-inch thick layer of cement treated aggregate, which would be a typical design for us on an interstate system. Based on what we learned from the NCAT test track, we came up with an alternative that consisted of 4 inches of asphalt, 6 inches of CCPR, again, the 2-inch open graded drainage layer, and then 12 inches of a reclaimed base using an FDR process. Using the two designs, we estimated the structural number using the ASH293 design as to be approximately equal, 7.08 for the original, 7.06 for the recycled design. But you see there's a huge cost difference. The expected cost for the traditional design, or the non-recycled design, was about $83 per square yard. The as-awarded price for the recycled design, again, the as-awarded price, ranged between $40 and $61 per square yard. And the asterisks that I show there is for the 12-inch stabilized foundation layer. In terms of where the existing pavement was in place and was reconstructed, that process was able to be done using an FDR process, or maybe a more traditional FDR process. And that part came in to about $40 per square yard. Where the new lanes were built, material was imported to the project, and in this case, crushed concrete. And that crushed concrete then was placed and then stabilized in an FDR process using the same equipment and following the same specifications as the existing lanes. However, because having to import material, the cost was higher. And for that section to work, it was $61 per square yard. Either way, significant savings from the $83 per square yard for the non-recycling design. So in terms of the recycled design for the I-64 projects, here's kind of a recap of what was done. For the new lanes, imported crushed concrete, or RAP, was used and stabilized in the FDR process. The contractor had the option to bring in either one of those materials, and they chose crushed concrete because it was available locally to them. A 2-inch asphalt open graded drainage layer was placed on top of the FDR, and then the CCPR was added on top of that. On top of the CCR was placed 4 inches of the 4-inch asphalt surface, and this is for the new lanes. Once traffic was shifted over to the new lanes, the existing lanes were addressed, and the existing base materials were stabilized using an FDR process, and then the same combination of OGBL, CCPR, and the 4-inch asphalt surface were added. I'll walk through a couple of photographs here showing the progression of the project. The first photograph here shows where traffic was pushed over a little bit to the right, so work could begin on the inside of the two lanes. Once material was brought into the project to produce the FDR layer, the foundation, the FDR equipment was brought in, and it's shown here doing the FDR process, again on the inside of the new lanes. Next, the open graded drainage layer was added, which you can see to the left of the pavement equipment. And here showing an example, this is, I believe, during a trial production of the CCPR material. So the CCPR was produced at a nearby mobile plant using the RAP that had been stockpiled from the contractors from various plants, was brought there, processed, and produced. The CCPR material was produced, loaded into trucks, and brought out to the job. You can see they're using traditional asphalt paper. I believe it had a high-density screed on the back, and they were able to place this material. Because the CCPR design was 6 inches, they placed this about 7¼ inches loose. and then compacted down to 6 inches. But they did place it all as one lift. After the CCPR was added, one layer of the asphalt overlay was placed on top, so 2 inches of asphalt was placed on top, and then traffic was shifted over to these new lanes. So the photograph showing here the 2 sets of inside lanes, that's the recycled material with the imported foundation processed with the FDR, CCPR on top of that, and vehicles are running on top of the 2-inch asphalt overlay. After this point, then the contractor was able to go through and start work on the outside existing lanes, but the outside of what's shown here in the photograph. So again, similar process, but in this case, once the existing concrete was removed, the FDR equipment was brought in to stabilize the foundation. And you can see on the other side of the Jersey barrier, that's live traffic that's running, 2 lanes of live traffic running on the recently added lanes. The FDR process was completed. The open graded drainage layer again shown here to the left of the pavement equipment, and the same process with the CCPR, where it's trucked to the project and placed in traditional paver. Again, same thickness for the material. And then a more recent photograph showing the project now. Again, 2 full width shoulders and 3 travel lanes on both directions. So this project, again, was about 7.2 miles per direction. When you multiply by the lane miles, it's about 72 or so lane miles. One thing we were able to do is just before the final overlay was placed, we did go out and collect a few cores to make sure everything was holding together and doing as we expected. And so the photograph here on the left is just where we took the core, and then the photograph on the right, of course, the core that came out. Given the size of the core, we had to break it in 2 pieces just to be able to get it out of the ground. So that's about 23 inches of material. And you can see the light color gray on the top is the 2-inch asphalt overlay, followed by the CCPR layer with the open graded drainage layer in the middle, and then the stabilized foundation below. So one of the things that we really want to do is we want to be able to understand how this pavement section is going to perform during its service life. One way we can do that is we can wait for observation of the pavement section, wait for it to do something on the surface, but there are things we'd like to know about how it performs under traffic and before we see any distresses at the top of at the surface of the pavement. So one way to do this is by instrumenting the pavement, where we can monitor the performance during the service life. So by using pavement instrumentation, we can measure the response to loading. We can assess the performance during the service and evaluate the design for future projects. This has really been a unique opportunity, and I'll take a quick second to thank. There are a lot of folks that helped with this project. I included a slide later, but this is a great opportunity. There are a lot of folks that helped make this project possible and helped get us the opportunity to come instrument this pavement section. And so many thanks to those who were involved along the way. This was a really unique opportunity. This particular section was the first pavement section that VDOT instrumented on the interstate system. There are other instrumented pavement recyclings. There's one other instrumented recycled pavement section in the U.S. that I'm aware of, and that's the NCAT test track. So that's again under test loading. As far as I know, this project was the first one in the United States that was done on the interstate for a recycled project. We were hoping to do the same thing when the I-81 project was constructed back in 2011, but at that time we concentrated a lot more on on materials characterization work, and so we did not instrument that pavement section. So at this time, as we're going through and assessing the performance of that project, we're having to rely on measurements such as ride quality, rut measurements, and also fall weight deflectometer testing. However, the pavement instrumentation, this I-64 project, will give us a lot more information along the way. So poll question number 3, how many pavement recycling projects on the interstate system include instrumentation in the U.S.? And it looks like for most that are responding, most folks are paying attention. And yes, as far as I know, this project on I-64 is the only one. If someone knows of others, I would like to hear about it. So moving on, this slide shows a plan view of the instrumentation that was placed on the Segment 2 project. We placed our gauges in 3 lines. The total array was laid out in 3 lines. So the dark line across the middle top of the figure is the edge stripe. So this would be the right edge stripe of the lane. The direction of traffic here is moving from right to left. And so the intent was, as a loaded vehicle would cross this, they would cross the circles, which are the pressure cells, before they cross the little eye hatches, which are the horizontal asphalt strain gauges, and then go on to another set of pressure cells. And this way we could monitor the performance of the pavement section, both in terms of pressure, in terms of strain, and also in terms of temperature and moisture content. So the round circles are the temperature probe array, the red dots, and the triangles are the moisture probes. A lot of this information we took as far as how to arrange the gauges here and where to place them, especially with respect to the center of the wheel path. A lot of that information we got from the folks, talking with the folks at NCAT and how they instrument their test track. And so, again, a lot of thanks to them for sharing that information with us. The next slide shows the profile view, and you can see we instrumented down through the pavement section. In terms of when we analyze pavement sections, 2 of the primary responses that we're interested in is strain at the bottom of the asphalt layer and also pressure on top of the subgrade. So as you can see, we place pressure cells on top of the subgrade. We also place on top of the drainage layer, but then we place strain gauges at the bottom of the CCPR layer. As I mentioned earlier, the OGDL was an asphalt stabilized drainage layer. Ideally, we would have wanted the strain gauges to be at the bottom of that layer, because that's where we expect the maximum tensile strain to be, at the bottom of the asphalt layers. However, because that layer was only 2 inches thick and the strain gauges are about 1/2 inch thick themselves, we thought there would be problems. In consultation with the contractor, they were not comfortable either with us placing these instruments before the OGDL was placed. And so what we did is we worked with them and we placed them at the bottom of the CCPR layer instead. And I'll show in just a few slides there what we did with that information. In terms of the actual instrumentation that we used, this is an advertisement necessarily for these sensors, but this is what we used on this particular project, and we've had good success with it on our accelerated pavement test facility as well. The data acquisition, you can see, was a National Instruments unit using LabVIEW software to acquire the data. The particular strain gauges, pressure cells, and thermocouples that we used are shown here. And again, we've had good success with those. The data processing was completed using a custom-built MATLAB routine that was designed by the folks that I work with at the Virginia Tech Transportation Institute. They were responsible for coming out and assisting me with the instrumentation and doing the data collection. So an example that I show of the data processing in MATLAB, the figure there to the bottom right is a trace, strain response trace. And you can see there are several peaks showing the compression wave ahead of the load, the tension force pointing down, or the tensile response pointing down for the load passing over the gauge, and then a compressive force following that. And each of these points is automatically picked in MATLAB for us to be able to do the computations. The installation of the gauges was tricky because, again, we were working in a live construction project. Fortunately for this project, things were made a little bit easier because, again, we weren't working within live traffic, but we still were working in an active construction zone. And so when we did the gauge installation, we divided it up into 2 parts. I'll go through and discuss it here verbally and then show a few examples and pictures. So the first part of the installation that we did was after the FDR was mixed, but prior to it being compacted. So as the FDR was mixed in the instrumented area, it was excavated in certain places for us to be able to place our sensors. And we placed pressure cells and moisture probes on top of and also 2 feet into the subgrade. Once the sensors were installed and the wires were run out to the side of the road, the material was replaced and then the layer was compacted as normal. After the asphalt open graded drainage layer was placed, but prior to the CCPR, we came back again and placed a series of strain gauges, pressure cells, and moisture probes on top of the open graded drainage layer. Then the CCPR was placed a few days later, and we observed the performance of the gauges during paving. Again, we had a lot of cooperation from the contractor here in terms of excavating material, and then also when the following layers were being paved. Many thanks to them. All the wires from all the instruments were collected in a junction box that was buried along the side edge of the road, buried to the top of it, was flush with the grade. And one thing to think about, and this was an area of concern that we had, was if instruments like this are installed with wires coming out in an area where guardrail is going to be located, it's so important to mark the location so the guardrail posts don't sever the wires. It's several days worth of work to do the instrumentation like this, and then to have it all go awry if someone puts the guardrail post in the wrong place, it's a huge disappointment. It would be a big loss, has been a big loss for us. In this particular location, we did not have guardrail, but I'll talk a little bit in a few slides about another project we did that was behind guardrail. So again, walking through some of the photographs of how we did the instrumentation work. This is the grade for the FDR. This is the existing material that will be processed for FDR, where our instruments will be located. We had a survey crew come out with a roving unit, GPS rover unit, and they came along and marked the approximate locations of where everything would be located, where our instruments would be located. And then the FDR process came along. In this case, the FDR was completed using cement. The cement was spread out. Again, everything done as normal. Cement was spread out, and then the reclaimer came along and processed, mixed that material to a 12-inch depth. Following the mixing of the FDR and not the compaction over top the area where we were going to instrument, we had a small small loader come out and excavate the material for us. The instruments were placed. We had the GPS rover come back, mark final locations for the instruments. The instruments were placed according to the plan that I showed a few slides back, and the wires were run off to the side in a trench to go to the junction box. Once all the instruments were placed for the FDR, the material was placed back and then compacted as normal. And you can see here the scientist from VTTI, she's working with the instruments in the data collection system, working with the wiring in the data collection system as a test as the machinery is moving over top of the layer. After the FDR layer was completed and the open graded drainage layer was placed, we came back for another round of instrumentation. So in this photograph, you can see the result. The open graded drainage layer is what's being shown here with our instruments on top. And again, the GPS folks from the contractor with the GPS rover came back, marked the location of the sensors for us, and then we installed our gauge arrays. Towards the top middle of the photograph, there's a series of 9 strain gauges and the 2 round plates toward the bottom of the 2 pressure cells on top of the drainage layer. Excuse me. A little talk about how we did the actual installation, especially for the strain gauges. The strain gauges really are the most delicate instruments, and to ensuring that they, stay where we want them during paving, and then also don't get damaged is something important. One way that we approached this was each wire that came off the gauge was encased in, you can see the flexible metal conduit acting as a protective sheath over the wiring. That was run all the way into from the end of the wiring at the gauge all the way to the junction box in that flexible metal conduit to protect the wiring during construction. Periodically, we cut sections of perforated hanger strap, wrapped it over the wire, and then used masonry nails to drive that, secure the hanger strap and the wiring to the pavement surface. Again, we did not want during the paving operation for the next layer for the paver to move these wires around and move the gauges out of alignment and out of place. Finally, you can see on the photograph on the right side, we added a mixture of hot asphalt binder and sand as a kind of a glue to stick the gauge down to the surface of that open graded drainage layer. Again, some of these processes are things that we picked up from working with the folks at NCAT, and some are kind of our own techniques that we've learned and have used on our accelerated pavement test facility. But using these processes, we've had good luck with gauge survivability. So far, if I remember correctly from all the instrumented work we've done, we probably installed maybe 100 or so of these strain gauges. We've had close to 100% survivability. After the construction work was completed and the road was finally open to traffic, this is probably about 6 or 7 months after we did the instrumentation work. We used a series of loaded VDOT trucks. We measured with portable scales all the tires around the truck, and then ran these trucks over top series of trucks across the instrumented section. We did not have a triggering system to fire up the gauges, but what we did is we ran trucks for about half a day each time we would go out and collect data. And then we had this camera system set up. Again, since it was live traffic, we really had to have a good way to know when the truck was actually going over the gauge array as opposed to any other vehicle going over top of it. And so we had this two camera system. One pointed a little bit upstream of the project to see the vehicles coming along, and then the next camera showing the vehicle going over top of the instrumented section. And that way we can go back in the data, and by comparing the timestamps from the camera and then the data collection, we can know exactly which vehicle was going over top of it. So it was important to, again, to coordinate and synchronize the clocks on those two sets of equipment. But this is how we were able to do the work. So again, the section was open to live traffic. Everybody was driving over who could. And then we had our fleet of VDOT trucks loaded to the known weights. So this photograph shows an example of the strain data. The data shown here shows a 3-axle truck going over top of the strain gauge. The dark blue strain trace would be directly underneath the vehicle tires, and the light blue strain trace kind of in the background is one of the adjacent gauges, but not directly underneath the vehicle tire. And so again, what we had to do is come up with a process where we had this entire gauge array and make sure we were capturing the, I guess, the most pertinent strain data depending on where the vehicle is located. So as I mentioned a little bit ago, the strain sensors were placed at the bottom of the CCPR layer, but ideally we'd like them at the bottom of all the asphalt layers, which would put it at the bottom of the open graded drainage layer. Through the construction process, we were not able to do that, but the way we actually calculated the strain at the bottom of the open graded drainage layer, and we did this by developing a layered elastic model, where we modeled the strain at the bottom of the CCPR layer, and we compared that to the strain that we actually measured using the sensors. We adjusted the inputs, the model inputs, to minimize these differences or to minimize the error, and then we used that model to calculate the strain at the OGBL, the bottom of the OGBL layer, or the layer of interest. So again, in terms of the layered elastic model, the inputs would be material stiffness and thickness, which we had the thickness from the core data that we took, and then we had ranges of stiffness values based on previous lab testing, and then we adjusted these again to minimize the difference between measured and modeled strain at the bottom of the CCPR. Once we were happy with the error minimization, we used that to calculate the strain at the bottom of the OGBL. So for each test date, we had approximately 20 truck passes. We focused on single axle dump trucks with about 20,000 pounds in the rear axle, and we measured the entire load of the truck using portable scales. So as the vehicles drove by, we had the camera taking a photograph of the truck. We knew exactly which truck number it was, and we used that data to correspond to the weight that we had measured earlier in the day. So to calculate the actual strain for each test date, we took the 95th percentile maximum strain from the gauge having the maximum average. So again, thinking there was a sensor array of 9 strain gauges, over the course of the one day, the gauge that had the maximum average strain, we took the 95th percentile of that strain from the multiple passes for that one particular gauge. And the reason for doing this is it accounts for the variability of the truck as it travels across that array. We did not have location marks on the road, and so we were asking the trucks to try to maintain, I guess, positional alignment as accurately as they could, but still it's difficult when traveling at highway speed. We also normalized the strain value with respect to the axle load and also with respect to mid-depth temperature. So here's an example of the temperature and load normalized strain. for the various test dates that we took. One of the things I found, I guess maybe the most interesting with this, and this correlates well to some FWD testing that we have taken on some other sections, is that you can see the trend of the strain is that it's decreasing with time. And this is something we expected to see with continued curing of the recycled material. So again, the trend was we saw a decreased strain with respect to time, which we expected. There is some variation in the strain. We think this is mainly due to positional alignment of the vehicles, which again is difficult from the live traffic. And this is the strain at the bottom of the CCPR layer. You can see here the average is maybe about 36 or 37 microstrains. We expect it to be a little bit higher at the bottom of the OGDL layer because again the maximum strain happens at the bottom of the asphalt layers. However, this is still a very low strain value. So just to try to further emphasize what we did, we wanted to compare the strain for the segment 2 section on I-64 with the strain that we measured at section S12 at the NCAT test track. At the NCAT test track, you can see the red and the blue arrows. In this case, the blue arrow showing the location of the strain gauges, and then the red arrow showing the location of the greatest strain. For the NCAT test track, those were in the same place at the bottom of the CCPR layer. But again, for construction reasons, for segment 2, the location of strain gauges and location of the greatest strain were in 2 different places, and we used modeling to try to account for that. Just looking at the 2 cross sections here, we would expect that the strain would be less on the I-64 section simply because it's a much thicker pavement structure. And we went through and we made our calculation. So the calculated strain at the bottom of the OGDL layer through the layered elastic modeling. We calculated an average strain of about 48 microstrains as compared to about 135 microstrains for section S12, the average at about 68 degrees F. So again, the 48 microstrains are calculated strain value at the bottom of the open graded drainage layer, whereas for section S12, the 135 is a measured value at the bottom of the CCPR layer. Again, the section on S12, the NCAT track, is approximately close to 30 million evils at this point. So we really expect, especially given the strain value, low strain value of segment 2 for I-64, that we expect to see a very long service life for that pavement section, especially with respect to strain performance. A quick recap of the data that I showed previously for the NCAT test track, and where I took the 135 microstrains from was the section strain data for section S12 at approximately 68 degrees Fahrenheit. So here's a summary of the I-64-2 pavement design. In this case, I want to highlight the amount of recycled material used on this project. Again, it was a little over 7 miles in each direction. In terms of the FDR work on the existing lanes, it was about 345,000 square yards. The cement-treated concrete wrap for the new lanes, again treated with an FDR process, was about 146,000 tons. And the project used almost 170,000 tons of CCPR. And again, in this case, the CCPR came from primarily stockpiled wrap that was located in the state. Overall, for this entire project, more than 500,000 tons of material was recycled. And we calculated an estimated cost savings of about $10 million in this particular project. Given the large amount of material that was recycled, the high cost savings for this project, we really consider this project a success. And we're also looking at the strain data we're collecting. We really expect a long service life from this pavement section. So in summary, pavement recycling can be used successfully on high volume traffic roadways. We have shown this from the example data we published elsewhere for the ID1 project, and what I'm also showing here for the I-64 project. We can also use pavement instrumentation to quantify structural performance. And for this particular project, we'll be evaluating the results over time and comparing the early and later results, and also comparing these to other sections, especially the NCAT test track. We also expect more information to come from this over time. I think some of these folks a little earlier, but I want to repeat, this work was only possible with the help of a large group of folks, more than I can name on one slide, so I list the organizations. Many folks in my office, colleagues at VTRC, VDOT personnel from the Materials Division of Hampton Roads District, the Virginia Tech Transportation Institute, Allen Myers Inc. is the prime contractor for Segment 2, the folks at NCAT and Auburn University, and also ARA. So poll question number 4, pavement recycling should be used on high traffic volume roads because the documented case of excellent performance, it's cost effective, better environmentally, or all the above. And looking at the responses, almost 100%, all the above, absolutely. I hope that's a huge takeaway from this presentation, all the above. There's some helpful links that I wanted to include in here, things that we found that were helpful to us and maybe helpful, some work that we've done that may be helpful to others. There's a series of checklists that are available by Federal Highway Administration for construction of these recycled materials. There's also great information available from roadresource.org where folks can go through and put in pavement condition examples of pavement deterioration and get suggestions on which pavement recycling techniques are most useful. Most of that's done in a graphical format and is so useful. So I really encourage you to take a peek at that. I was also fortunate to be part of the project team for NCHRP 951, the NCHRP 951 study, and a final report for that, a link is included. And that's all on material properties of CIR, CPPR, and FDR. And the intent with that was to develop model inputs for mechanistic empirical modeling using the MEPDG process for these materials. The final report for the 962 study was recently published on looking at process control and acceptance tests for recycled materials as part of the 962 study. And again, a link is included here. I'm assuming these will all be available at the end of the presentation. Another great source of information is the Basic Asphalt Recycling Manual published by ARA. The figure on the right shows the most recent copy, the 2015 one. 2001 is a good version, but again, the 2015 one is an updated, and there's a lot of great information in that. So I encourage you to locate that document, and if you can't, if you don't have a copy of it locally, you can get a hold of an ARA contractor, and they can supply those for you free of cost. Also, the next webinar in the series is the Series 2 Crack Seedling that will be held March 18th at 2 o'clock p.m. Eastern Standard Time. And below is the link to connect to the or sign up for the webinar. Thank you so much for your attention during the presentation and for attending. I'd be happy to address any questions. If you have further ones, my contact information is listed here, phone number and email. Please feel free to contact me. Thank you so much.
Thanks, Brian. Well, we got a little bit of time. Let's go through our chat and see if there's any questions that we can answer. Before I do that, I want to take a little bit of time here. Brian's presentation is available on the file share there, as well as upcoming webinars that we're working with as a partnership with PPRA. So please feel free to download those as appropriately, as well as our evaluations. I really respect everybody's time and would appreciate it if everybody could take the time to go through these evaluations. We use this information for us to assist in future webinars, so any assistance on this would be greatly appreciated. See if we can minimize this chat button. It's kind of a little bit too big for us. I've taken over our evaluations. Thank you. And when you're going through the evaluations, use a little small arrow with a little line to go to the next slide, With that said, let's go through some of these chat questions there, Brian.
Jason, do you want to read them off? Because I was the one responsible for maximizing that, so I could see them.
No problem, Brian. No problem. Confession's always the first thing. Okay. Hopefully everybody at the beginning was able to hear fine, and it all worked out well for everybody. There was a question by Danielle Gorin that he made a comment regarding the typical traffic volumes that were depicted, and I'm not sure exactly what specifically he meant by that, but he had a comment there, Brian, about your typical traffic volumes that they were depicting. Not exactly sure what was meant by that.
Yeah, so I guess the number that I showed was 44,000 vehicles per day and 5% trucks. That's the directional traffic. So in one direction, that's what we see. I think that was I forget now, that was eastbound or westbound. It was a little higher in the other direction. And in one portion of the project, I think it approached 46,000. 44 was the average across the 7 miles. But yeah, that's a 2019 traffic data.
We had somebody raise their hand. If David could allow Bayed to speak his question, I'd appreciate it.
Oh, yeah, absolutely. Ladies and gentlemen, to ask a question via the phone, please press *1 on your telephone keypad. A voice prompt on your phone line will indicate when your line has been opened. Please be sure you pick up your handset before pressing the corresponding digits. Once again, *1 to ask a question via the phone. We'll pause for a moment.
Thank you, David. So, Biped, Shah, did you have a question? Feel free, *1.
So far, nobody's queued up for a question. Once again, *1.
Okay.
No questions in the queue.
Thank you, David. We had a question by Kennedy. How is FDR considered recycling? And I responded back to them on that one, Brian, and pretty straightforward. Jacob Malowski had a question. Was the S12 FDR layer stabilized? If yes,
it was.
What type of additive?
It was stabilized with cement. If I remember correctly, 5% cement. So that would be the existing aggregate base and the top of the existing subgrade there at the test track.
Thank you, Brian. Eleanor had a question. How is this widening and reconstruction project impacting the movement of freight?
Well, I-64 serves as a major corridor, I would say. Again, this is out of my area as a pavement engineer, but I-64 is a major corridor from the Port of Virginia carrying goods out of that area to the rest of the state and elsewhere. So it's a huge impact. And the reason the widening work was done because this is a major bottleneck area, and as traffic is increasing, you're really looking at expanding I-64 in some capacity almost all the way to Richmond. I don't remember the mileage there, but it's probably close to 40-some miles. So they're looking to expand it ultimately, I think, all the way to Richmond for traffic capacity reasons. In the summertime, it's a popular route going to and from the beach in the Outer Banks and Virginia Beach area, and then also for hurricane evacuation for that portion of the state. They actually have the capability to reverse the inbound lanes and have everybody go outbound. And so adding more capacity there is certainly a safety feature as well.
And then Brian, she added, will there be any long-term benefits, particularly for freight coming from the Port of Norfolk?
Well, I assume in terms of reducing delay due to adding the extra lanes and extra capacity in the roadway, I'm sure that predictability on their travel times would be very important to them.
Right. We had Hamid from the city of Edmonton. He said, we have done many filmed FDRs in Alberta, Canada, and experienced longitudinal cracks in 1 year after construction, both on highways and city roads. Any similar experiences from other agencies and any suggestions?
It'd be hard for me to suggest, I think, anything without knowing more about it, but I don't know if it was a, given the location, if it's a cold temperature crack or exactly what it might be. We have not had similar experience here, but again, our climate is much different.
Maybe a little information about what the subgrade and subbase material were, what kind of soils had been an issue. Then we had a question from Brad Schneider. What was the makeup of the FDR section? Particularly depths or percentages of asphalt, stone, and soils, and then what percent of cement was utilized?
So again, on this project, the segment 2 on I-64, the FDR process was used on really two different kinds of materials. In the new lanes, it was all using all on imported material. So it was really creating a cement stabilized foundation. So again, the contractor imported crushed concrete. It was stabilized using cement, but it was using the FDR process. So using the FDR equipment and also following our state FDR specifications. And so that's the main reason I'm calling it an FDR layer. In terms of the reconstructed lanes, once the concrete was moved, the material that was exposed was reclaimed with the FDR process. So it was the existing aggregate base in the top part of the foundation. And I don't have the exact numbers in front of me, but I'm assuming that 12-inch depth is somewhere around probably 80% aggregate base and the rest of it being subgrade material. Although the exact proportions I don't have in front of me. There were a lot of designs done on that material. Again, as you can imagine, over a 7-mile stretch, there were a lot of changes. My understanding was there were close to 200 designs done for the FDR process by itself. But I think they settled somewhere around, for the most part, about 5% cement. I understand there were a lot of places it was a little bit higher and a little bit lower. But I'd say probably on average it's in 5% neighborhood.
All right, Brian, we have another question from Eleanor. Will any of the recycling techniques or gauges employed in segment 2 of the project be used in segment 3?
So thank you for reminding me, Eleanor. I should have mentioned this. So the segment 2 work was completed in 2019, and segment 3 is underway. Actually, last summer we went and installed a very similar set of gauges in segment 3, so we'll be able to monitor that section as well. So operationally, the two segments are administratively different. And so when we did our work, they were separated by that, but we do have gauges in both sections.
Thanks, Brian. Comment responded back from the city of Edmonton. He responded that their specs require a 1% cement in foamed FDR.
So did you say in foamed FDR, Jason?
Yeah.
So yeah, that would be typical. When we do, especially with the foamed asphalt material, we would also include a little bit of cement along with it. In terms of the process we use here on the I-64, the FDR was the primary stabilizing agent with cement.
And it looks like Craig Rayfield had a response about the FDR section, and thanks, Ray, for supplying that information. Appreciate it. Irvin had a question about his experience with FDRs for highways and runways. No launching or cracking with foamed asphalt or no. So no cement was used for their FDRs. Okay, thanks, Irvin. And again, one of those things that I mentioned there on those ERA sites, the helpful tools, there are guidelines for FDRs and CIRs and others. So feel free to use that ERA site as much as you can for further information on guidelines. And then we had Marshall Thompson respond back to Brian about what was the strength of the FDR with cement. Any idea?
So thanks, Marshall. That's a great topic in and of itself. Our FDR state specifications are unique, at least from the agencies that I have worked with. We actually have when a cement FDR project is designed, we actually have a strength window on the compressive strength value of 250 to 450 psi, and we required the contractor to develop a design to stay within that window on a 7-day break. And so the thinking for us is we don't want that material to be so stiff that we end up with shrinkage cracking later on. And so I don't have the numbers in front of me. If you're referring to the model maybe that I developed and the stiffness value there, I can get back with you on it. I just don't have it right in front of me. But as far as the design work, they work to stay within the 250 to 450 psi compressive strength window for the design. And again, I think that's a unique component to our FDR spec, and I don't know how many other states do that. I think a few do, but not very many.
Along that same question, Brian, I had a question for you. With your FDR, with your cement, are you doing any kind of proof rolling for that shrinkage cracking?
No, we do not.
Thank you. Sally Houston had a question. Is the open graded DL virgin HM? Virgin HMA? Open graded dense layer, I believe. Is that correct, Brian?
The open graded drainage layer, that material is all virgin. That layer is produced with all virgin materials. And if I remember, it's a 50% blend of I think it's 68s and 8s, if I remember correctly. On our website for VTRC, there's a report that was done probably, I think when it was, 2012, 2013 neighborhood by Bill Maupin. It talks a little bit more about that material, but it's 100% virgin material.
Thank you, Brian. Another question, and I'm sorry if I pronounce it wrong. Zhang Li, great work, Brian. Your strain gauges were placed longitudinal direction. Did the NCAT pencil strains used for the comparison come from the longitudinal direction, not in the transverse direction?
In the longitudinal direction, yes.
Okay. And then she says, I am asking this question because there was a significant strain level difference between your data and NCAT data.
Yes, but there's also a significant difference in terms of the pavement thickness and thus the pavement stiffness, too.
Thanks, Brian. Had a lot of kudos from everybody saying great job, so that's great. Bruce Ware had a question. Was there any requirements for the wrap that was imported for the CCPR layer?
So there was a gradation requirement and a top size requirement, but I don't think there was, and I don't know if Craig's still on the line, he would know better than I would if there was another requirement beyond that. I don't think, there's, as far as I know, there's nothing about fracture faces or percent binder or things like that on the wrap material, but I think it was mainly the gradation requirement.
Thanks, Brian. I had a question here from Bipad again, Sahia. I'm sorry if I pronounce it wrong. He said, how can we get the critique of FDR and the FHWA in pavement design? Not sure what he's exactly saying there, Brian. How can we get the CRETID?
Maybe the credit?
Maybe. FDR and the FHWA pavement design.
Yeah, Peapod, I think the answer to that is really, you think about the FHWA, the MEPDG process, there's two sides of it, the mechanistic and the empirical side, the M and the E. The mechanistic side is what we're able to cover with the instrumentation to look at the pavement response, and the empirical side is all the distress responses or predicted distresses. And I think it's going to take more information like these instrumented sections and the test track sections and things like that to be able to come up with that side. And I think once we have that kind of information, we'll be able to better credit the FDR material.
Along with that, Brian, he mentions also, or she, it was linear in AASHTO 93, meaning layer coefficient. Okay, we had another question for Zoe. And are the FDR and CCPR applications with asphalt emulsions or foamed asphalt?
So in this particular project, all the FDR was completed using cement only as the primary stabilizing agent, and the CCPR was completed using 2.5% foamed asphalt and 1% cement.
Thanks, Brian. And Craig responded back to the CCPRM was a foamed asphalt. Marshall Thompson had another question. Was any FWD data taken over the gauges?
No, not yet.
Not yet. Stay tuned.
Stay tuned, exactly.
Hannah had another question from the City of Edmonton. It is almost on majority of our FDR projects that we use 1% in FDR. Cracks are longitudinal, not transverse, and not on the wheel pass. Okay?
Interesting.
Yeah. For Jesse Bone, Ahmed, Florida does a lot of foamed FDR. Do you know anybody down there? If not, I can try to find you a contact, so provide you some information. And Ahmed says, thank you. Jesse Bone also said, do you only see cracks when the temperatures are low? Maybe it's going with the information from Edmonton. He might be responding back to the gentleman from Edmonton, maybe. All righty. All righty. Let's see. Craig had another response saying, as a contractor, we sent all the wrap through a screening system to get us much more consistency gradation to assist with the control of density. That's good. And ITS values for testing CCPRM. Thank you.
Thank you, Craig.
All right, and that kind of wraps it up. Well, I had one other one came in here, Brian. Steve, problems with a non-wheel path longitudinal cracking could be related to improper longitudinal joint construction. Very good point, Steve. Yeah. With that said, anybody else, any further questions for Brian?
Once again, star one if you'd like to ask a question via the phone. We'll pause for a moment.
A lot of kudos, Brian, for a good presentation. A lot of people enjoyed it. Appreciate it very much.
Thank you.
And with that said, that kind of wraps up our webinar today. Any final comments, Brian?
No, again, thanks for the opportunity to talk about our work, and thanks so much for attending.
Well, that wraps it up for today. Thank you for all attending, and we look forward to seeing you next month. Have a good rest of the afternoon.
And that does conclude our conference for today. We thank you for your participation and for using AT&T teleconference service. You may now disconnect.